We're supposed to verify whether lines L1 and L2 are parallel or not parallel. To do that, we can use theorem 2.11 from our text. The theorem tells us that we can have a parallel line to a vector A, B, C. Okay, we can describe a parallel line to some vector A, B, C, and where A, B, and C are the coefficients of t. Okay, so here the coefficient of t is 1, so A equals 1. I've got that from this part of the formula. Okay, the coefficient of t when we're dealing with y is 1 as well. There's no number in front of t, so it's 1. And then c is 1. So if we examine the vector 1, 1, 1, then L1 is parallel to that vector according to theorem 2.11. Okay, so whatever this line is, it goes through a different point, but this line is parallel to 1, 1, 1. Okay, and we can do the same thing with L2, except L2 is just in a different form. L2 is in the form of a symmetric equation of a line. Okay, where we're equating all the x, the y's, and the z's together, all those three different directions. And so the vector that we were talking about at the beginning, a parallel vector, is A, B, and C down here, right? So in this case, if we want to finish putting it in the form of a symmetric equation of a line, usually it's being divided by some constant at the bottom. So since there wasn't any written, we can divide by 1. That doesn't change it. So this vector is also parallel to 1, 1, 1. So since L1 is parallel to 1, 1, 1, and since L2 is parallel to 1, 1, 1, then L1 must be parallel to L2. These lines are parallel to one another. And so if the lines L1 and L2 are parallel, find the shortest distance between them. Okay, let me pull up that theorem. So we've determined that they are parallel. So if you try to visualize vectors in three-dimensional space, I think usually we have it go out this way. Draw the two vectors. Maybe one starts over here and one starts over here, and you can visualize this coming out at you, coming out from the computer screen. We just want one point to pick here on this vector, and then we can use the distance from a point to a line, theorem 2.12, to help us find the fastest distance to the other point, because we're going to involve a cross product, right? A cross product helps us find right angles, between vectors or planes, and so that's going to help us find the shortest distance from this vector to this vector. So it really can be any point. You could start here, you could start over here, you could start from this line and come over here. So all we need to do is identify some points on both lines, and then we have already our directional vector. They're both going in the same direction, so they both have directional vector v. So now we just need to pick points P and point M. So, and we also are supposed to identify a line L. You could pick either one. You could say this is your line L, or you could say this is your line L. Okay, so we'll just stick with the first one. This will be our line L, and we need to identify a point P that it passes through. So the easiest point to identify is 1, 0, 2, right? This is the parameterized version of a line, and using that form, we know that point P, a point that it passes through, is 1, 0, 2. And then M needs to be a point not on line L. Okay, so we could check just to make sure, but a quick one would be 3, 1, 3 coming from our second line. That's a point that's, well, unless by coincidence, it's not on line L. They'd have to be the same. Yeah, they would have to be the same line for them to be the same, right? We just found out that these are parallel, and as long as they're not the same line, then this point 3, 1, 3 will not be a point on line L. So we need the directional vector PM. So that's real quick to do. Take the x component of M subtracted by the x component of P. So 3 minus 1 makes 2, 1 minus 0 makes 1, 3 minus 2 makes 1. And now we're ready for the formula for the distance. Okay. The distance is going to be the magnitude of the cross product of PM and our directional vector V. So we saw in our text that the text uses a determinant of a matrix to help us find the cross product, where you put IJK across the first row, PM is going to go across the second row, and directional vector V goes across the third row. And then down here it's the magnitude of V. That's a quick calculation, right? Square root of 1 squared plus 1 squared plus 1 squared, so that's the square root of 3. So all we need to do is evaluate that determinant and then the magnitude of that resulting vector. So the magnitude, the determinant of this matrix, there's plenty of videos to help with, if you're not sure how to find the determinant of a matrix, like this week's lecture video, I'm pretty sure we go through one of these cross product calculations. So for the ith component, I'm finding the determinant of this smaller matrix. So that's going to be 0. And I need to subtract the j component, which is, oops, I want to get rid of that other. There we go. Subtract the j component, which is found by a determinant of the matrix made of these two columns. So it's 2 minus 1 makes 1. And then plus the k component, which is found by finding the determinant of this smaller matrix. So that's 2 minus 1 makes 1. And that's all over the square root of 3. And then you could rewrite that vector into whatever form you want in case you're having trouble reading that. That's 0 for the ith component, 1, and 1 here. And so again, that's just a magnitude calculation, just like we did before. 0 squared plus 1 squared plus 1 squared is 2. So it's the square root of 2 over the square root of 3, or the whole thing just square root of 2 over the square root of 3.